Hello, and I welcome to you all to this tutorial session. So this is the eighth tutorial session on the topic of power system engineering, and I will be dealing with a tutorial session regarding this. So before I start, I would like to introduce myself. I am Mohd Owais Khan, Prime Minister Research Fellow at the Department of Electrical Engineering, Aligarh Muslim University. So I hope you have gone through the lecture, NPTEL lecture of week 8, and in those lecture you have gone through load flow analysis, how we calculate the load flow, and also voltage stability indexes has been studied over there. Indexes, okay. So we will be briefly discussing this, and then we will solve questions regarding this. Okay, so we will start with some of the questions with it. Okay, so basically, voltage stability index, it is actually gives an idea regarding the stability of a distribution system. It is actually voltage stability index. So basically, it gives an idea about the stability. It is derived, firstly, it is derived based on power flow equations. Power flow equations in a radial distribution network. It assesses the stability stability of any bus, like how stable that bus is. Okay, so it is, so how it is calculated, let's consider Let's consider a two bus system. Okay, and it is a radial two bus system. So what happens here is that here, let's say power flows from m minus bus to mth bus. Let those buses are m minus 1 and mth bus. The impedance line impedance, let's say, is equal to Z is equal to R plus JX. Sending end voltage, let's say, is equal to Vm minus 1. Receiving end voltage, receiving end voltage, let's say, is in Vm. And power demand at bus M, it is, let's say, it is PM plus JQ. So what happens here is that, so the apparent power which flows from m minus 1th bus to mth bus, what it will be? Sm is equal to Pm plus JQm. So the current in the line will be current in the line. It will be I is equal to Sm conjugate divided by Vm. And what is Sm? Sm conjugate is P minus JQm divided by Vm. So if we apply Ohm's law, then Vm minus 1 is equal to Vm plus the voltage drop. Vm minus 1 is equal to Vm plus, what is that? R plus Jx. It is multiplied by Im, we just calculated, Pm minus QJPM divided by Vp. So what will be here? Vm minus 1 equal to Vm plus R. R will be multiplied by R into Pm minus J R into Qm divided by Vm plus J X into Pm divided by Vm plus Qm X by Vm. So if we rearrange the above equation, we get Vm minus 1 Vm R Pm plus Qmx divided by Vm plus J Pm into X minus Qm into R divided by Vm. Okay, so if we these are the this is the imaginary part, okay, and this is the real. So what we do, we square on both sides. It will be v square m minus 1 vm whole square. Okay, and what we can do here, we take the squaring on the real part. Okay, this then what we next is the v square. We take only this part here and then we square it. So it will be equal to 2 PMRX 2 RPM a square plus b square. The b square will be this much, the second term. P square plus qm square r square plus x square divided by vm square plus 2 into pm rx plus qmx, but vm and vm will get cancelled out because 2ab ab it will get cancelled out. So basically it will become like this. So if we rearrange this, so it will come out to be how much? So for stability, VSI will come out to be VSI. The expression of VSI you must have seen in the lecture also. It will be VM4 minus 4 times PM x minus QMR square minus 4 VM square PM R plus QMX. So whenever we ask to calculate the VSI, we should use this formula. Okay, in the detail you can see over there, but I have write it here so that you should have an idea how we are going to solve it, because in the sum of the questions we will be using this formula to calculate the VSI. And for the VSI, if we generalize it, like say we generalize it, so it is already you can change the x or r for, let's say this is m, this is m minus 1, like this. Here one of the thing is that if VSI is greater than 0, the system is stable. This is the most important thing. If we after calculation, and if it is close to 0, it is close to collapse, means it is marginally stable, you can say. And if it is negative, then we can say it is the system is not stable. Okay, and that's why this formula is widely used in the determination of the VSI. So we will solve questions here, because theory is not so much here in this, because we will solve some questions based on that. We will understand how these formulas are going to implement, because just derivation is not going to help us. So we will start with first question. So the question is, a node with high voltage stability index is, so the options are more prone to voltage collapse, B, less prone to voltage collapse, C, always unstable, D, stability cannot be ascertained. So write in the chat box what will be the answer to this. I just told you about that. A node with a high voltage stability index is, the first option is more prone to voltage collapse, less prone to, always unstable, or stability cannot be. Basically, if a voltage VSI is higher, means it is positive and higher, it is less prone to collapse. Okay. So basically for this, the option is less prone to the voltage collapse. Okay. So the next question here.
Sir, please explain, sir, how it is. Collapse means voltage deep.
Yeah.
Collapse means voltage deep, no? Voltage se gaya.
Actually, collapse is a misnomer term. Just a second. Okay. Actually, means is that voltage collapse means just like, you know, I would say the correct word here is that node is not stable. Okay. But the question has been asked about this collapse, so we can relate that to. Okay. So basically, just a second. So basically what happened here is that if the index, what is the index? Index is about the voltage stability, VSI. For let's say there is a 33 bus system and we calculate the voltage index for each one of that. Okay. So what happened here is that if the VSI of any bus is less than 0, it means it has already means it is not stable. So what happens here is that it may have been outages, or it in near future the outages, that node will not be able to withhold the load attached to that, so there will be outage occur. But the thing is that if it is like say if there are 33 values, and if I say which of the node is more prone to unstability, so what you will see here, you will check that which node has a lesser VSI. So that will, if we add extra load to this node, then it will lead to a outage. Actually here it means outage. Okay, it's just a misnomer term, because in the question it has been collapse. So collapse means like that if we add more load, or in future due to consistent loading on that node, it will lead to a outage problem on that node. So that's the meaning of collapse here. I hope you understood that. My audio, my audio clear to all of you?
Yes.
Okay, just a second. It's not going for my. It's still coming to you, audio?
Yes, you are audible clearly.
The next question is here. Mm, a DC ring main distributor A B C D A is fed from 280 volt supply as shown. The resistance of each section AB, BC, CD, and DE, EE is 0.180 per 100 meter. The loads are connected as shown. Find voltage at C and D. Okay, so basically this is AB, this is A, this is B, this is C, D, E, and the loads are connected here with a loading 30 ampere, this is 20 ampere, 280 volt is here at this point, and 40 ampere is going here. This is the supply at the A, and the cross sectional length of each is AB is 240 meter, BC is 260 meter, and CD is 280 meter, and DE is 320 meter, and EA is 220 meter. So we have to uh, calculate the uh, you know voltages at C and D. Okay, so let's solve this solution. So let's assume that the in the currents in the section A to B and going from A to B, let the current is X, capital X. So let the current in the section A to B is X. Okay, X ampere. So if we apply here, so what happens here is that let me redraw that thing over here again. Okay, so AB, the current is X. Then after that, 40 ampere goes here. So in the B and C, the current will be X minus 40, then D, E. So in C to D, what happens here is that another 10 amperes goes from here. So remaining X minus 50 will be here. Then again 30 ampere goes from here to there at the D point. So it is 30 ampere. What happens here? The remaining current means X minus 50 minus 30, which is 80 will be there. Then again 20 ampere goes here. So remaining current will be X minus 100. So we have to find the value of X. Okay. So what we do here, we will apply KVL. Apply KVL A, B, C, D, E, A. Okay. So it's simple. Let's say this is X into R AB, section resistance between AB, plus X minus 40 into R BC, the section resistance between BC, plus X minus 50 into section resistance R CD, plus X minus 80 into section resistance R DE, plus X minus 100 into section resistance R EA is equal to 0. So first we have to calculate the section resistance. Now what happens here is that RAB is equal to how much? AB is the 240 meter, and I have given in the question for every 100 meter the resistance it will be 0.18. So if we can say here for like it is given here for every 100 meter. So for every meter what it will be 0.018, okay, ohm. So if you multiply it for 240, if the resistance will come out to be, I think, just a second. There is a problem in the question, I think. Okay, just a second, let me solve it. I think in this question it should be given here per 100 centimeter, because the solution does not correspond to that. So it will be 100 centimeter per 100 meter, maybe. So okay, no problem. That's not an issue. You whatever you given in the question, you can solve it. Okay.
Yes, sir. It is given, sir. It's per 100 meter.
But per 100 meter it is given. But if we implement it, the solution. Let me just a second. Per 100 meter. So for 2.240 meter will be what it will be. Okay. For 100, this is not like it's not a direct multiplication, no? So we can change it like no problem. Let's see, it is 100 meter. So we can multiply it, okay? So it will be 2.4 into Just a second. 240 first. 240 into 0.0018. I think I am correct. No, one more extra. 0.018. I think it is right. Okay. So because the solution will be different. Okay, no problem. It's just a calculation issue, nothing more than that. So as how much it will be? Just a second. Give me the answer in the in the chat box. It will be 4.32, I think. Oh, yes. Okay, so now solve it for RBC. RBC is equal to actually, what happens here is that when you get a solution to this from NPTEL, their value will change because in that solution they have taken a different thing. So that's why I'm saying per meter. Okay, no problem. Uh, That's not an issue. कोई issue नहीं है इसमें. Just it's just a calculation thing. So next will be how much is BC? It is 260. It is 260. So let me calculate it for that. 260 into 0.018. How much value is it? Give me in the chat box. It is, I think, 4.68. Okay. Am I correct or not? Okay. I think yes. It is 4.68. So similarly calculate for RCD also and RD. Give me the answer. I'm just checking one thing. Okay. What are those values for RCD and R?
Sir, one thing, one doubt. So
Uh,
0.1 it is per 100 meter. Then per meter it is coming around point 0.18 divided by 100 into 260. That is coming around 0.468 rather than 4.68.
yes. That's what 100. Yes, exactly. That's what I want. Okay. Wait, oh, it is double zero. Okay, na?
Yes, double zero.
Yeah. That's why I'm confused. Why it is coming so much high? 1 0. Yes, it is great. Now it is good. So it will be point zero four. What it will be? 432. Okay. Yes. It should come this way. That's why I was confused why it is coming so high. Okay, yes. Okay, now RCD. Which is RCD? RCD we have length is 280. So 280 multiplied by how much? 280 multiplied by 0.0018. So it will come out to be 0.504. And similarly for RDE, it will become out 320 320 multiplied by 0.0018. So it will be 0.576. And similarly for RE, how much it will come out to be? It will simply, if you multiply it with, 220, 220 into 0.0018. So 0.396. Yes, now it's correct. That's why I was saying why it is coming high. So basically, it will be, yes. So all these values are correct. Yes. So if we put these values, so what will happen here? X into 0.432 into x minus 40 plus 0.468 into x minus 50 and plus x minus 80 multiplied by what it is 0.504 into x uh, plus 0.468 into x minus what I have done 0.432 into x plus x minus 40 into 0.468 plus 0.504 0.504 into x minus 50 plus x minus 80 0.576 plus x minus 100 0.397396. Okay, 396 equal to 0. I hope I have written the correct equation because in changing the slides it's get distracted. Okay, yes. So if we solve it for x, it's a simple equation. We can, take x terms one side, 0.432 plus 0.468 plus 0.504 plus 0.576 plus 0.396 equal to other values 40 into 0.468 plus 50 into 0.504 plus 0.80 into calculate this value, okay, by using a calculator and write in the chat box 100 into 0.396. So if we add this, what it will be? Give me the answer in the chat box at least. Add these values, okay, 0.432, 0.468. Using the calculator. क्या वैल्यू आई? No one. Right hand side value. Okay, let me 129.6 and yes, x into 2.376. So if we divide it, what it will be? 129.6 divided by 2.376. So the value x comes out to be 54.54 ampere. Okay, I think up till now everything is clear. Now we have to find, but we don't have to find the x. We have to find the value of voltage at C and D. So what it will be? So VB is equal to VA minus X into RAB. It's simple. VA we have given 280. X we just calculated. Multiplied by RAB we just calculated 0.432. So based on that, if we calculate the value, it comes out to be 256.44 volt. Similarly, we calculate C, so it will be VB minus X minus 40 into RBC. What is RB? VB 256.44 minus X minus 40, 54.54 minus 40 multiplied by RBC, which is 0.468, I think. Yes. So based on the VC comes out to be, if you calculate that, it comes out to be 249.634 volt. You can check by using the calculator. If not coming, then write in the chat box. I will solve it for you. It's a simple calculation. Similarly, VD, it is VC minus X minus 50 into RCD. Okay, what is VC? It is, we just calculated. Okay, always cross check these values because sometime calculation error occur on my side also. Okay, because I have to teach and write both things at the same time. So what is RCD? It comes, we just calculated 0.504. 0.504. So if we calculate VD, it comes out to be 247.346. Okay, we can also calculate VE, which is VD minus X minus 80 into RDE. Similarly, and it comes out to be 262.01 volt. So you can clearly see that VA voltage is 280 because at that point it is supply is given. VB is 256.44. VC is 249.63 and VD is 247.34 and VE is 262.01. So you can see here that if I ask another question, at what node the minimum voltage occur? You can see that at the node D, the minimum voltage occur. It is another question we can frame here. Okay, okay, great. So this is how we have solved this question. I hope you have understood clearly. So now next question. The distribution system S1 and S2 are represented as sending end and receiving nodes, and their nodes values are given. So system 1, sending end, receiving end, PL and QL. They are given in KW, KVAR. ठीक. So first 1, 2, 3, 4, 1, 2, 3, 4, 5, and 6. Receiving end 2, 3, 4, 5, 2, 3, 4, 5, and 6. Okay, the values of PL is 32, 28, 27, 23, 21, 18, 16, 12, and 13, and 9. Okay, for the same system, the and nodes are 1, 2, 3. Let's say, and into second system, system 2. The PL and QL are same kVAR and kilowatt. These values are how much? It is 35. This is 20. This is 20, 22, 20, 15, 10, 13, 15, and 10. So what we have to find here, all the lines in the system have same impedances. So we have to calculate all the lines. First, all the lines in the system has same impedance. It is given in the question. Both system actually. Okay. We have to find which of the following has worst voltage stability index. Okay. The options are here. System 1, B, system 2, C, cannot be determined. You have to give me the answer, all of you. D, both have same VSI. Give me the answer. Okay. एक सिस्टम दिया हुआ है सिस्टम 1 and 2 इसका लोड कनेक्टेड टू दीज receiving end node 2, 3, 4, 5, 6 has been shown here. Okay, so basically what the question has been asking, which of the following has a worst voltage stability index? So I will give you a minute to think upon that. You have to give me the answer that which system has a worst voltage stability index. No one? Okay, so actually what happens here is that voltage stability, as I have told you about, it is dependent upon the A. Okay, it is dependent upon the connected load. Okay, the system connected load demand. Okay, let's say a system has a load demand of 32 kilowatt, 32, and it is another load demand of 40. So what happens here is that the nodes in this system will get, the voltage profile will become more poor if we add more load. If we add, let's say, 20, if we add 20 to both, so I can clearly say the load on the second system is higher. So it eventually lead to a worse voltage profile, and worse voltage profile will give an indication that that system has a worst voltage stability index. It clearly shows that. So what we will do here, first we will calculate the load demand. Okay, so first, system 1, PL1, it is 32, 27 plus 21 plus 16 plus 13. So it will come out to be 109 kilo. Then QL1. So it is 28, 23, 18, 12 plus 9. So it come out to be 90 kVA. Okay. Now for the system 2, PL2, it is 35, 20 plus 20 plus 10 plus 50. It come out to be 100. Then we calculate for 2. It is 20 plus 22, 42, 15 plus 13 plus 10. It come out to be 80 kVA. So you can clearly see that the system 1 has a higher load in comparison to a load demand on a system 2. So what happens here is that its voltage profile will be worse because the demand on the system 1 is higher. So if if voltage profile is worse, which shows that the voltage stability index is also worst. Why? Because if we add extra demand, let's say about 50 kilowatt and 50 kVAR, then the this system 1 will become has a more worse voltage profile. Okay, it's quite self-explanatory, I think. So basically, the answer to this question is what? System 1. Yes, system 1 has a higher load demand, so its voltage stability index will be lesser. Okay.
So that means more demand, that is more worst.
Okay. What?
More demand, uh, that implies that there is the worst system. Is that correct?
वर्स सिस्टम इन टर्म्स, एक्चुअली उसको हम इस तरीके से कहेंगे कि इट विल, व्हाट इट विल डू हेयर, कि जब लोड डिमांड ज़्यादा होता है, ठीक है, तो वोल्टेज प्रोफाइल जो है इट गेट वर्स. रीजन इज दैट, व्हाई? बिकॉज इफ द लोड डिमांड इज हाई, देन वी नीड, then the feeder current will gets high. Okay, because we have to supply the demand. Based on that, voltage drop will gets increased. So what happened here is that voltage profile gets worsened. Okay, it deteriorates. And voltage stability index ये बताता है, it shows that how stable your system is. Okay, I just in starting shows that it shows the stability of an any node. If overall voltage profile is deteriorated of a system, then that voltage VSI of that system will become worse. Okay, am I clear to you?
Yeah.
Okay, that's the thing. And it's I just starting I also show is assesses the stability of any bus, mean how stable that bus is. So basically, and demand of any network is high. It means it means that it needs higher feeder current. And in radial system, generally, what happens here is that the feeder current flows and will lead to a higher voltage drop in the system, which lead to a poor voltage profile. Okay, I hope this is clear to you. Now, moving on towards the another question. Okay, one thing is which I want to say here. See, what happens here? We just solve the question just before. Okay, here, what we see here, we saw here that at the source when the supply is given at A, and in the consecutive nodes voltage gets dropped, and you can see here at voltage D we have the minimum voltage. But at voltage E, the voltage gets increased. Why? Because it is due to the radial nature. Because let's say if this A and E is not connected, then the voltage of E will get much lower than the voltage of D also. Okay, so that's why in the radial networks, okay, if I have given two network, a radial network and a unilateral, or I would say a lateral network. If someone asks me which of these two network which will have a better voltage profile, I would clearly say the radial network will have a better voltage profile, as you can see in a just above question. Okay, see here. As this is the source node. After that you can see voltage start decreasing, but after D voltage gets increased. Why? Because E is connected to A, and it is the radial nature of that. If E is not connected to A, I would clearly say its voltage will become less than 247.34, whatever the voltage of D here. So basically, what I want to convey here, that if a network is lateral, its VSI will always be less than the network which is a radial. Okay, so VSI of radial is always greater than the VSI of a lateral network. Okay, why it is so? Why is it so? Because in a lateral network, what happens here is that it is not connected unilaterally. Okay, in a unilateral network the current flows like this. Okay, but in a radial network, like in a IEEE 33 bus system, like it is like the here. So if let's say this is 34th node, okay, if I place in a lateral network, it will come after 33 buses. But let's say substation bus. Okay, so what happened here is that it is closer to a substation in a radial network. Okay, and so what will happen here? Its voltage profile will be much better. But if I change it into a unilateral, this 34 bus will come after the 33 buses. So voltage drop will get higher. Same is the case we have seen here in the question we just solved. So basically, what I want to say here, one important thing, radial network. Just I will write it here. It's a very important point. VSI, the voltage stability index of a radial network is much higher in comparison to a lateral network or unilateral, a network which is connected node wise in a lateral way, lateral network. Okay, why is it so? I just already explained to you, and we have seen in the question also. So let's move on towards another question. Okay, so the question here is, consider the given radial distribution network. It has a line data and bus data both. So 1, 2, 3, 2, 3, 4. It is sending end, it is receiving end. R, X, PL, and QL. It is kVAR. This is kilowatt. This is ohm, and this is also in ohm. Value is 2.5, 1.2, 2, 1.004 in 2.5. So 300 load attached to that, 200, 250, and we have 150 and 120 and 60. So here loads are connected to RE nodes. Okay, this thing you should keep in mind. This 300 and 200 is connected to second 3 4 2 3 4. Okay, and we have to find the voltage at bus 2 after the first iteration. Find the voltage at bus 2 after first iteration. Okay, so I will solve it for you. So basically, if we redraw that here, it is 2. Just it is not needed. Let's just solve this. So kV base is given here. Actually, one thing more. Base voltage in the question is given 1 11 kV, and base MVA volt ampere. Base VA volt ampere is given 1 MV. Okay, so let's solve this question. So Z base is what? Z base is, we know, kV square base divided by MVA. Sorry. Here kVA 11 into 11 divided by 1, it will come out to be 121 is the Z base, and initial voltage is given is 101 per unit. Okay, so Z1 is R1 plus J X1. So what is 2.5 plus 1.2 J? If we convert in per unit, then we divide it by the base value. We know that it is this much. So if we solve it, it come out to 0.207 plus J triple nine. I, this I think it comes out to be. Let me check it, the value for it. 2.5 divided by 121. 0.027, yes, it's correct. And 1.2 divided by, yes, 0.009. Okay. Then similarly on the same similar lines, we calculate Z2, which is 2 plus J divided by 121. It comes out to be 0.0165 plus J 0.083. Okay. Then we calculate Z3. These are all in per unit because we have divided it with the base. Z3 is 4 plus 2.5J divided by 121. So it's come out to be around 0.033 plus J 0.0207 per unit. So these are the per unit values of impedances. Then PL2 plus JQL2, which is the apparent power. So it comes out to be 300 plus J 200 divided by, this is in kilowatt. Okay, this is in kilowatt. So what we will divide it by a kilowatt. So MVA is given 1. So we will divide it by 1000. I hope it is correct to you. Zero point 0.3 plus J zero point 0.2. On the similar line, PL3 plus JQL3. 250 plus J 150 divided by 1000 comes out to be 0.25 plus J 0.15. These all are in per unit. PL4 plus JQL4. It comes out to be 120 plus J 60 divided by 1000. It's come out to be 0.12 plus J 0.06 per unit. So we have successfully converted all those values in the per unit values. Initial values we will take P loss, all initial values of losses is 0, and we have to iterate for first iteration. Okay, so basically P2, you should know this formula: PL1 PL2 plus PL3 plus PL4 plus initial values. Okay, these all comes out to be 0.67 per unit. Then we calculate Q2 at 2. It comes out to be 0.41 per unit. We will Q2 plus QL2 plus QL2 plus QL3 plus QL4 plus initial values of losses, which is this much. So it is 0.41. Now we will calculate a matrix which is P2R1 plus Q2R1 X1, sorry, minus zero point 0.5 V1 square. This you have seen in the lecture when we do the load flow analysis using the forward backward sweep method. So if we calculate it, what is P2? 0.61 into R1. What is R1? R1 is 0.027. Okay, 0.0207 plus Q2. Q2 we just calculated 0.41 into X1. What is X1? 0.0099 minus zero point 0.5. V1 is 1. Okay. So if we calculate it, it comes out to be minus 0.482. Okay. This is A1. Down a similar lines, we calculate D1. Okay. We calculate D1. So how we are going to calculate D1? It has a formula: A1 square minus R1 square plus X1 square, then P2 square plus Q2 square raised to the power 1 by 2. So if we put this formula in here, it's just a simple formula. Okay, and these we calculate in a load flow analysis of a radial distribution system. A1 Based on that, it will come out to be 0.4817. We just have to put the value we whatever value we just calculated. Okay, it's nothing sort of like that. Now we calculated what we calculated d1. Now after this we will calculate the voltage v2. Okay, how it is calculated at the next bus? How we calculate the next bus? It has a general formula. Let me write its general formula also. It will help you understand. dm1 underscore a m1 square minus r square x square p m square plus qm. This is 2. Okay. Then we calculate the second. Second is simple as that. Under root, we just calculated d1 minus a1. Okay, of the voltage at the next bus, or we can say node, which is 2, which we have to calculate. So based on that, we will solve this question. And d1 0.4817 minus a1 is minus minus plus, so it will come out to be 0.4821 under root. If we solve it, let me solve it for this. 0.4817 plus 0.4821, it comes out to be under root this one, and if we under root it, it come out to be 0.9817 per unit. So V2 is this much. So the value come out to be, okay, uh, 0.9817. In the options, there are four options given. You can see the third option will be correct. Okay, I'm not writing the options here, just a wastage of time. I will move on towards the next question. Okay, which is very much important, which will question number whatever it is. I think leave that thing. So what is the next question? A figure. Mm, okay, the figure shows the figure shows a 220 volt secondary system. Okay, wait a second, let me draw the system here, then we don't have to write anything else. This is first node, this is first node, this is second node, this is third, this is fourth. Okay, and the loads are connected to second. It is 50 ampere at the rate 0.85 power factor lag. Then it is 20 ampere at the rate 0.95 power factor lead. At fourth, it is connected 30 ampere at the rate 0.9 power factor lag. Okay, and the branch, let's this branch resistance is given zero point 0.1 plus J 0.05. Of the second is Z23 is given 0.08 0.08 plus J 0.02. Third is given, just a second, it is given here, it is given here, and it is given here. Okay, so these are given. So let me write it down here. Z1 is zero point 0.1 plus J 0.05. Z2 is zero point 0.08 plus J 0.02, and Z3 is zero point 0.2 plus J 0.08. Okay, V1 at this is 220 with angle 0. Okay, and these currents, let's say this is I2, I3, and I4. So I2 will be 50 at the rate power factor 0.85. So if we write it, we can write it in the minus 31.788. I think I have written it correctly. If not, you can write in the chat box. Okay, these are the value of the current I1, I2, I3, and I4. Okay, so what we have to find here, we have to find the, in the question, we have to find the voltage across the feeder point 1 to 4 using approximate analysis method. Okay, so voltage drop contributed by each load is voltage drop by each load. We have to calculate the voltage drop by each load. So VD1, what it will do? I into Z. It's quite clearly. Okay, the current magnitude is 50, and if we multiply, how much? Just a second. Okay, so first we will take the voltage drop. Voltage drop due to load tapped off. Due to load tapped off from point 2. Okay, it is equal to 50 into 0.10 plus 0.85 plus 0.05 into 0.527. Okay, what we done here, we multiply I into Z. Okay, And if we calculate this, it will come out to be 5.5675 volt. Okay. Now we will calculate voltage drop due to load tapped off from point 3. इसकी वजह से कितना आएगा? We will calculate it. At that point, the magnitude is 20. Actually, what we can do here, we can also change these values like this, okay? Then multiply it, or we can change into complex and multiply it, okay? Anything will do. We just use the we just have to use the calculator. Is I think more very much okay. Just a second. 0.08 plus 0.01. Yes, okay. So if we take the voltage taken off from here, then the current line will be this much. So we have to add the real part, then we will add the imaginary part. Okay, 0.08 plus zero point 0.1, then 0.02 plus zero point 0.05. Then the whole Z will become Z1 plus Z2. What I have just done here is this. Okay, it's just a simple thing. Then it multiplied by 0.95 minus 0.02 plus 0.05 multiplied by 0.3122. So it's simple. It will come out to be 2.9833 V. Or we can do here, what we can do here, we can add both Z1 plus Z2 and change in this angular form and multiply it by I3. Either thing you can do. Okay, it's just a simple calculation using a calculator. Now again, voltage drop due to takeoff from point 4. Now what happens here is that when we will take the voltage drop from here, then the line length will become Z1 plus Z2 plus Z3. It's simple. So it will be 30 into zero point 0.1 Z1, zero point 0.08 Z2, zero point 0.2 Z3 multiplied by zero point 0.9. Yes, zero point 0.9. Imaginary part, real part multiplied by zero point 0.9 minus, just a second, sorry, plus 0.02 plus 0.05 plus 0.08 multiplied by 0.435. Okay, it's simple. It come out to be 12.21 volt. Okay, now we have to calculate the total voltage drop from load 1 to load 4, load 1 point to load 4. So what we do here, we just add all these 5.56 plus 2.98 plus 12.21. If we add it, it comes out to be 20.7 volt. Okay, it's just a simple question. I hope you have understood this question here. Okay, now we will solve another question. Okay, a DC ring, a DC main main ring distributor is supplied through AB feeder. Okay, the loads are tapped off loads are tapped off at C, D, and E are tapped off. Okay. A interconnector is placed between C and E points. A is feeding point and maintained at 300 volt. The resistance per 100 meter length of feeder, the resistance of per 100 meter length of feeder AB is 0.15 ohm. Ring distributor ring distributor is zero point 0.2 and interconnector 0.25. Find the current flowing through the find the current flowing through interconnector CE. Okay, एक फीडर है AB. It is supplying a DC main ring distributor. Okay, and the feeder length is, I will write, I will draw that feeder first. This is A, this is B. Okay, and this is a feeder of length 250 meter. Then it is supplying to a DC main ring interconnector. This is C, this is D, this is E, and this is F. The length is 100 meter, 100 meter, 200 meter, 3, 200, 150, and there is an interconnector between C and E, which is also of 250 meter. Loads are taken off at C, which is 20 ampere. At D, it is 10 ampere. At E, it is 25 ampere. At F is 30 ampere. Okay. Okay. So we have to find the currents in the CE. So let's assume AB is a feeder. So AB is a feeder. Its resistance value is different. Its resistance value, let's say the current in this section, let's say the current in this section is I. Let's say the current in this section is I. Okay, from A to B. Let AB section current is I from A to B, and in section BC it is X times BC. C section of distributor, meaning it is X ampere from B to C. Okay, and in the section BF, this one it is, let's say, Y, and in the section CE, let's say it is Z from C to E. Okay, so basically this is Y, this is X, and this is Z. So we will apply KVL in B, C, E, F, P, A. Okay, apply KVL in B, C, E, F, B. What it will do? BC X into RAC plus Z into RCE plus Y into, just a second. Yes. So plus Y minus 30 into how much? REF plus Y into RFB. But here, what we have taken here, Y is in the this direction, but we are going in the opposite direction. So basically, what we will do here, instead of plus, we will write minus here. Okay, or we can say here, just remove the minus, it will be equal to this. Okay,
So what we have considered from E to F, that
uh,
is X is for BC and Y is BF and C
y
is Z.
yx is for BC, from B to C, and CE, from CE it is Z, and from BF here this is Y, direction from B to F. Okay, so basically it will come out to this. Now what is RAC? We have to find RAC. RAC, sorry, sorry, RAC not, it is BC. RAC तो कुछ भी नहीं है, RB into C. So in the question it is given resistance per 100 meter length of feeder, for the feeder के लिए दिया हुआ है इतना, which is a AB, but I would say this is length, और and ring distributor के लिए है 0.2. So basically it will be 0.002, 0.002 into BC is 100. It will come out to be zero point 0.2. I think it is correct. You can cross check it. Okay. Then similarly RCE, it is also, it is an interconnector. So its value is different. So it's 0.25. So 0.0025 into 250. So it will come out to be how much? Let me calculate it. 250 into 0.0025. It's come out to be 0.625. You all cross check these values because it may be possible I might mistakenly put it in wrong way. Okay, REF, which is also again a ring distributor. So it will multiply by 100, so it will come out to be zero point 0.2. Then RFB, it is also again a ring distributor. It is a 150, so it will come out to be 0.002 into 150. It come out to be zero point 0.3. Okay, so basically point, what will happen here? Okay, so zero point 0.2 x minus zero point 0.7 y plus 0.625 z is equal to minus 12. Okay, I think it is correct if we put on these values. 30 into zero point 0.3, yeah, zero point 0.2, yes, 4. Just a second. One thing is REF. Just a second. REF is 200. That's why it's problematic. It is 200. So this value is zero point 0.4. That's why 12 will come over here. Okay. I think this equation is correct. Then we are again apply KVL because we have three variables. KVL in loop CDEC. Okay. So in CD, X is here, minus Z goes there. So remaining current will be X minus Z minus 20. Same current will go here, but with another 30, another 10 ampere deficit. C, D, E, C, D, E, C. Then again, we are taking the current here. We know what's value of the current is here. That is Z multiplied by this. Okay. So again, we apply KVL. So first it is X minus Z minus 20 into RCD, okay, plus X minus Z minus 30 into RDE, which is equal to how much? Z into REC. Okay, what is RCD? It is 0.002 into 100. Okay, it will come out to be zero point 0.2. And RCRDE, it is also a ring distributor, 0.002 into 200. So it come out to be 0.40. So X minus Z minus 20 into zero point 0.2 plus X minus Z minus 30 into zero point 0.4 is equal to Z into, what is REF? REC is 0.625. Yes, 0.625. So let me multiply it for you. It will be X will be zero point 0.2 plus zero point 0.4, okay, minus Z 0.2 plus zero point 0.4 minus 4 minus 12 is equal to Z into 0.625. So X term will be 0.6x and Z term will be minus 0.6z. Minus 16 is equal to 0.625 z. I hope until now you are quite clear. If we rearrange this, 0.6x minus 0.625, it will 1.225. Z is equal to 60. So this is the second equation. Okay, so we have first equation, second equation, then we know also we have to need another equation. So what happens here is that, as you can see here, if we know that input current is equal to output current, whatever is coming inside will be equal to the output. So what is output here? 20 ampere is going at B, at C, 10 ampere at D, 25 at node at E, and 30 at the at F. These are all the output. Okay, and the coming current is how much? It is equal to I, because from feeder I this much amount of current will be come. So it will be around 30, 60, 85 ampere. Okay, so the input current will be 85. So basically 85 will be here, and this 85 will distribute in such a way that it will go on like this. So 85 at node B, at node B, at this node, 85 is equal to x plus y, because at this node 85 is getting distributed to x plus y. So we got the third equation. So basically what we have, first equation, let me write it over here. First equation, 0.2x minus 0.7y plus 0.625z is equal to minus 12. Then we get another equation, 0.6x minus 1.225z equal to 16. Then we get another equation, x plus y is equal to 85. Okay, so if we put, we have to find the value of this z. So let's, x is equal to 85 minus y. Put this in all these equations. So 0.2, 85 minus y minus 0.7y plus 0.625z is equal to minus 12. So it will come out to be, let me calculate it. It is 17 minus 0.2y minus 0.7y plus 0.625 z is equal to minus 12. So it will come out to be minus 0.9y plus 0.625 z is equal to minus 19. So if we take the minus sign off, it will be like this. Okay, then if we put x 85 in this value, zero point 0.6 into 85 minus y minus 1.225z is equal to 16. So zero point 0.6 into 85, it will come out to be 51 minus 0.6y minus 1.225z is equal to 16. So 0.6y minus 1.225z is equal to 51 minus 16. It will come out to be 35 minus, and if we remove that minus sign, so these values will become positive. So this is, let's say, fifth equation, and this is the fourth equation. Okay, so using these two equations we will solve it. So what, we can rearrange the fourth equation, rearrange fourth equation and it will be equal to y equal to 19 plus 1.625 z divided by zero point 0.9. Okay, I think it's quite clear if we take this here and divide it by zero point 0.9. So value will become out to be y is equal to 21.11 and 0.625 divided by zero point 0.9, it will be plus 0.694. Okay, this value put in here. We will solve it for z. Okay, so 0.6 21.11 plus 0.694z plus 1.225z is equal to 35. So basically it will come out to be 12.66 plus zero point 0.6 into 0.694, it will be 0.4164z plus 1.225z is equal to 35 plus 1.225 equal to 35. If we solve it, so basically it will come out to be, let me solve it for you, divided by 1.6414. So 1.6414 Z is equal to 35 minus 12.66. So 35 minus 12.66, 22.34 and divided by 1.64. So Z value divided by 1.6414, it comes out to be around 13.61. Okay. Based on that, we can say this is the value of the current which will pass through the interconnect. If there is any calculation error, because I have not solved this question, I have solved just as it is in front of you. Maybe some calculation error, but you can check it and you can correct it. Value may change, but the steps to solve this will remain same. That does not changes. Okay, so these are all the questions. We will solve some other questions next week also of the new topic which you will be taught in the NPTL. So if you have any question regarding this, you can ask. And with this, I end today's lecture. I hope you have understood this and have a better understanding to how solve these type of questions. But these are some of the questions because limitations is here. You can solve some question on your own, and it will lead to your better problem solving activities. With this, today I end today's session. Thank you for all joining. If you have any question, you can ask. Otherwise, you can leave. I will wait for a minute or two. Thank you. So, thank you for all coming here. We will meet again next week.